You are audible.
Okay. Yeah.
Thank you, sir, for sparing your time.
Yeah.
Can we wait for 10 minutes for because still people are joining. People are joining.
Yeah. Right. You can wait till maybe five, five, five or so.
Okay, sir. Okay, sir. Then we will start in 5 minutes. No problem.
Your university is in Kolkata, is it? Okay.
Yes, sir. Our university is in Kolkata.
Yeah. Yeah. So you are all mainly it will be undergraduate students who are attending.
Yes, sir. Maximum students here are from UEM Kolkata, and most of the students are undergraduate students.
Okay.
Some students, some attendees are from IITs and other universities also.
Okay.
Uh, so, thank you for sparing your valuable time and accepting our invitation to spare your valuable time as a speaker of our event. Thank you, sir, and we can start the webinar now.
Yeah. So shall we start now?
Yes.
Thank you for the IEEE student branch and Samanway for extending this invitation to deliver this talk. And the topic for today's talk, as you may all know, is MEMS and nanotechnology for and their aerospace applications. So, can I share the screen?
Yes, sir. Yes, sir.
Just give me a moment.
Yes, sir.
Is the presentation visible?
Yes, sir, it's visible.
Yeah. So the topic, as I already told, is MEMS nanotechnology and their aerospace applications. I have borrowed this material from a few of my senior colleagues also. So that is what is listed as acknowledgements at the end. So let us see the basic outline of the talk. The first, I will start off with an introduction to MEMS. Then we will deal with some MEMS case studies and applications. Then an introduction to nanotechnology, because MEMS and nanotechnology are the topics that we are going to deal with today. The applications of nanotechnology, specifically its applications in space. Then the current status of nanotechnology research in India, and finally conclusion. So these MEMS and nanotechnology, as you may know, are two of the promising new areas where a lot of research is being carried out all over the world as well as in India. And they have got quite a good number of applications, and they are supposed to revolutionize the world uh, in the in the recently, that is in the recent future, and therefore that is why these topics have got a particular relevance. So let us start off with an introduction to MEMS. So MEMS is an acronym for microelectromechanical systems, as many of you may know. It is a platform technology to create tiny devices. It is an offshoot of semiconductor industry. That is, it is a branch of study which has evolved from the semiconductor industry. It leads to an integrated microsystem on a chip. It's a new way of making complex integrated mechanical systems with electronics. So what you have to take care of here is that it is a way of integrating mechanical systems along with the electronics. The ICs, as we know now, the integrated circuits are mainly used to integrate electronics onto a silicon die. And what MEMS gives us is the power to integrate some mechanical elements also. So they can act as sensors, they can act as actuators. So these are the main applications or the main areas where the founders of this technology have seen. Uh, so the technology drivers, as we see over the previous few decades, if we see, it is the memory chips in the case of in the decades of 1970s, digital computers also. Then we came across processor chips in the 1980s, then network chips leading to internet in the 1990s, wireless chips and mobile devices in 2000, and integrated sensor chips and wireless sensor networks from the year 2010 onwards. So now also, even though one decade is past, even though from 2010 onwards we have been seeing this trend of integrating the sensor chips also onto the silicon substrate. Now also the work is going on to integrate the sensors as well as the electronics onto a same substrate. So this work is ongoing now also. So what are integrated microsystems? An integrated microsystem is a complex microsystem with diverse functional blocks such as electronic circuits, mechanical actuators, optical devices, chemical and biological sensors, etc., assembled on a single substrate or package. So what you have to take care of here is that not only electronic circuits, but mechanical elements such as actuators, optical devices such as mirrors, those kind of devices, chemical devices such as chemfets leading to gas sensing, etc., and then biological sensors. That is, some sensors which, for example, can do a lab function. They are all integrated onto a single substrate or package. So that is the integrated microsystem, which gives us tremendous power in the sense that we are able to integrate mechanical elements, optical elements, chemical elements, etc., onto a silicon. It may not be silicon exactly, onto the same substrate or package. That is the power which the technology gives us. So there was a lecture by name. There is plenty of room at the bottom, and it came in the form of Feynman's challenge in 1959. That is, you must have heard about the physicist, the famous physicist called Robert Feynman. So what he predicted is that information in a page of a book can be written in an area that is 1 by 25,000 times smaller in linear dimension. He can construct a rotating electric motor which is only 1 by 64-inch cube. So that was a challenge which is met in 1960. So basically what he predicted is that there is nothing that I can see in physical laws that says the computer elements cannot be made enormously smaller than they are now. So basically he foresaw the miniaturization as we are seeing now. And this is the ability to manipulate matter at the atomic scale, and it will have enormous technological and economical impact. That is the basic prediction which Feynman did. So this basically became true, even though the prediction happened long back in 1959. What we are seeing is that it has become true, and especially true by the invention of the technologies such as MEMS. So MEMS-based sensors, if you see, it is a microscopic electromechanical structure fabricated using silicon as basic material. It includes structural elements such as cantilever, beams, diaphragms, cavities, etc., which serve as mechanical components. Then embedded piezoresistors or deposited capacitance also serves as electrical component. The advantage of these sensors, that is the main thing, signal conditioning circuitry can be integrated along with the sensor in a single chip. That is the main advantage of the technology. That is, it gives us the power to integrate the sensor and the associated signal conditioning circuitry on a single silicon chip. And such small chips are generally referred to as smart sensors. So the sensors are fabricated using micromachining techniques similar to IC fabrication. So what is the novelty in this? The novelty lies in the fact that microelectronics exploits only the electrical properties of silicon. That is, in the case of microelectronics and VLSI, we are exploiting only the electrical properties of silicon, whereas in micromechanics, we take advantage of both electrical and mechanical properties. That is, the mechanical properties of silicon are also used. So why do we choose silicon? It is as light as aluminium with the strength of steel. It is highly sensitive to stress and temperature, which makes it suitable as a sensing material. That is the main thing. It makes it suitable as a sensing material. With the present day technology in IC industry, it is possible to manufacture. So this is another major point. When we are borrowing the technology from IC industry, it is possible to manufacture an array of devices on one wafer, which makes it amenable to batch manufacturing, and therefore it reduces the cost of the devices. So this is another important point to keep in mind, that the technology, because of its evolution from microelectronics, makes it possible to or makes it amenable to batch manufacturing, which makes the system cost, which brings down the system cost to a very small value. So this is very important because, as we know, if the technology has to find use in commercial applications, then definitely need to be low cost. For example, our smartphones itself integrate a number of MEMS elements, some of you may know. But if they are going to be costly, then you can just imagine what kind of cost one smartphone will have and how many of us will be able to afford it. So for any technology, it is highly essential that it should be amenable to manufacturing, and manufacturing in an economical, low cost way. So that is where technologies like MEMS has got an edge. So components for MEMS, microsensors, microelectronics, microactuators, and microstructures. These are the major components of MEMS. So functions of MEMS components, each of these microsensors, they gather information from environment. We are having different sensors like chemical, thermal, biological, optical, etc. Microelectronics, it processes the information derived from these sensors and it also drives the actuators. Then microactuators, they respond to commands from microelectronics in order to move certain parts, moving, positioning, pumping, regulating, etc., and controlling the environment for a desired outcome. Then a microstructure is basically a packaged product or system. So basically what we can see here is that sensors, electronics, actuators, everything is integrated onto a single small or tiny microsystem. So the advantages of MEMS, as we have already seen, can be manufactured using batch fabrication techniques. Unprecedented level of functionality can be obtained on a single silicon chip. Reliability and sophistication, low cost, improved performance to cost ratio, and it leads to a miniaturized total system. These are the advantages of MEMS. So now we come to the next part, that is MEMS case studies and some applications of MEMS. So basically, I am going to show you a few examples of some MEMS sensors which we have realized in our organization also. So the first example is in the form of pressure sensors. They get a pressure input, and the transducer or sensor produces an electrical output, and it may require an excitation in the form of a voltage also. So this depicts the basic functionality of a pressure sensor. So, going a further detail into the block diagram, we have got the applied pressure, which is applied on the metal diaphragm, which creates a stress field and which induces a resistance change in a strain gauge. And there is a Wheatstone bridge configuration, as you might have learned in your undergraduate courses. The Wheatstone bridge configuration is used to pick up the resistance change, and the Wheatstone bridge, of course, needs a supply voltage or excitation also, and then we get the output voltage out of the bridge, which is directly proportional to the applied input pressure. So that is the basic functioning of a pressure sensor. And if you see the output voltage versus pressure, if you plot it, then we can see that for different voltage excitation values, we will get linear curves. So this is basically a linear transducer, which gives an output that is linearly dependent on the input pressure. So this is a MEMS pressure sensor which we have developed back in ISRO. It has got a pressure range of 0 to 1 bar. It has got a proof pressure of 2 bar. It has got a bus, that is basically the proof pressure is the pressure, maximum pressure that you can apply without degrading the sensor characteristics. Then it has got a burst pressure, that is a damaging pressure of 4 bar. It typically works with an excitation of 5 volt. It has got an output span of 4 volt, and the sensitivity of the sensor is expressed as 3.9 to 4.1 volt per bar. That is, for 1 bar change, we get a 4 volt, a nominal 4 volt output. It has got a zero offset of 0.6 volt, and these are the accuracy figures of the sensor. It has got a nonlinearity plus hysteresis figure less than 0.3 percentage, and the hysteresis figure itself less than 0.1 percentage. So these are the typical specifications of a MEMS sensor. So the applications is in automotive industry, MEMS pressure sensors are used to measure engine oil pressure, transmission fluid pressure, tire pressure, etc. MEMS pressure sensors are also used in biomedical applications, process industries, gas exploration, oceanography, aerospace, rocketry, etc. So these are the major uses, and this is one of the major categories of MEMS sensors that are in commercial use today, that is pressure sensors. So the features are, as we have seen, can be manufactured using batch fabrication techniques similar to ICs, design of small geometries, precise dimensional control, design flexibility, interfacing with control electronics, repeatability, reliability, high yield, low power, and low cost due to mass production. So that is those are the major features of the MEMS sensors. So how does miniaturization help us? That is basically what this slide is about. Miniaturization allows us to make small systems that move or stop quickly due to mechanical inertia, low mechanical inertia, and thus ideal for precision movements and for rapid actuation. So it is good for precision movements. Miniaturized systems encounter less thermal distortion and mechanical vibration due to low mass. They are having a low mass, therefore less thermal distortion and less mechanical vibration. Miniaturized devices are particularly suited for biomedical and aerospace applications due to their small sizes. Small systems have higher dimensional stability at high temperature and therefore low thermal expansion. Smaller size of the systems means less space requirements, so this allows packaging of several functional components in a device. Less material requirements also mean low cost of production and transportation, and they are readily mass producible. So these are the main advantages that we get out of miniaturization, which all of us may know from our day-to-day, even from our appliances which are used for day-to-day applications. But these are the major advantages of that. So how do we fabricate? Earlier in the case of pressure sensors, we told that there is a metallic diaphragm. So how do we fabricate this diaphragm? It is done by using a process called bulk micromachining. It involves deposition of sensing element by sputtering or evaporation, then etching of bulk silicon to form the diaphragm, and piezoresistor is the sensing element which is used in these pressure sensors. So this graphic basically shows how the diaphragm is manufactured onto the silicon die. We will not go into much details of this. What we can see here is that a cavity is formed in the basic silicon die, and there is a glass sealing which is done over that cavity, and the metal diaphragm is deposited over this cavity, And when the pressure is applied, we can see that this diaphragm will deflect. And the deflection of the diaphragm or the strain on the diaphragm leads to a resistance change by the piezoresistive property of the material which are deposited, or resistance devices which are deposited, resistive devices which are deposited from the substrate. So this is how the pressure transducer basically works, and this is basically a cross-sectional view of the same pressure transducer, which shows the pressure pot on the back side, it shows the etched cavity, then it shows the silicon diaphragm, and then a p-type diffused piezoresistor also, and then metal conductors. So this pressure sensor will be packaged, or will be electrically configured into a bridge, as we can see in the bottom diagram. The resistors R1, R2, R3, and R4 are the piezoresistors which we get out of the pressure sensors. So any variation in this R1, R2, R3, R4 will lead to a voltage Vout which is directly dependent upon the resistance values. So that comes from the basic bridge theory, as we may all know. So packaging is a major challenge in MEMS technology, and another important aspect of MEMS technology. The package, what does it do? It lends mechanical support to the device, it lends electrical interface, it gives environmental protection, it gives media interface free of fluid leaks, then mechanical stress isolation. A low-cost, small packaging solution compatible with standard manufacturing process is required in order to make the MEMS devices or market the MEMS devices. So this basically shows a MEMS device integrated onto a package. As you can see, the device with its bone wires. The bone wires is what you see here, taken all onto the bone pads, and that leads to the electrical connection to the outside world. And there is a mechanical encapsulation also. So this is the basic graphic corresponding to the MEMS pressure transducer, and here we see a cutaway view of that, and we can see basically the metallic diaphragm, and then the piezoresistors which are deposited on the silicon, and then the leads which are coming out of the sensor in order to provide a electrical connection to the piezoresistive element. And now we look at a second case study, which is a smart pressure sensor, which we have realized in our organization. It is basically a MEMS sensor integrated with intelligent electronics. When we started off the lecture itself, we told that one of the major features of this technology is that it gives us the capability to integrate sensor along with its associated electronics. So we can put in any electronics. We can put in a computer, a microprocessor, so that we get some intelligence also, so that the sensor data can be processed along with the sensor. So another important advantage that it gives is that it gives a temperature compensator output. Then it gives an RS485 serial output port. It has got a built-in transducer electronic datasheet. It gives miniaturization using 3D packaging techniques, and it has got a very small size of 57 mm length and 28 mm diameter with a weight of approximately 100 grams only. So this is basically a miniaturized smart pressure sensor which integrates the pressure transducer along with the associated electronics. Now, if you take a look at the block diagram, electrical block diagram of this, it will basically look like this. It has got a pressure sensor, then a temperature sensor also. Remember that we have told about temperature compensation, and for these sensor values are acquired by using an analog to digital converter, as you may have studied in your undergraduate courses also. And then there is a microcontroller which gathers the data from this analog to digital controller, analog to digital converter, and then this RS485 transceivers are used in order to establish a serial output port to a downstream system. So basically, it has got a serial wired capability. So that is what the pressure sensor is. Now, what is the thing that temperature compensation that we told? It is one of the basic data processing techniques which is useful especially on with pressure sensors. In the case of a normal pressure sensor, here as we can see, when the temperature is varied, the pressure reading will also vary. As the blue curve shows here, we can see that the pressure reading varies according to temperature also. So the reading is dependent, the output voltage is dependent not only on the input pressure but also on a parasitic component such as temperature. So we want to make, for an ideal sensor, we want to make the reading insensitive of the temperature. So what we do is something called temperature compensation, and that is some sort of data processing which is done by using the microcontroller inside the smart sensor. And after that is done, we can see that basically the pressure reading is constant with respect to temperature. That is basically the variation of pressure with respect to temperature or variation of reading with respect to temperature is nullified by using the compensation scheme. Then another commercially very successful device in the MEMS arena is the MEMS accelerometer. So it is a number of devices are introduced which are compatible with silicon IC technology. They enable batch fabrication and low cost, possibility of single chip solution to enhance resolution. It is one of the most successful MEMS product in the market and has got wide applications like in automobiles, shock and vibration sensing, laptop hardware protection, spacecraft systems, etc. Now, this is the basic working principle as far as the mechanics is concerned. This is the basic working principle. It has the sensor has got a C-spring mass or something similar to a C-spring mass, and there is a spring and there is a dampener. So there is an equation that is associated with this system of a spring, dampener, and a mass, and that relationship is given by the second order equation of x divided by a is equal to 1 by s square plus s into omega r by q plus omega r square, where omega r is equal to root of k by m. K is the spring constant and m is the mass. That is the resonant frequency, and q, the quality factor, is equal to m omega r divided by b. So this is basically a typical spring dampener mechanical system, and that is what constitutes our MEMS accelerometer also. So this is another look at the analysis of MEMS accelerometer. Here we can see that basically we get that x by a is equal to m by k, which is the sensitivity. What is that? X is the deflection of this proof mass, a is the applied acceleration, m is the mass, and k is the spring constant. So here we can see that the sensitivity is given by m by k, and the resonance frequency is given by root of k by m. So basically what we can see here is that these are in contrast. That is, when we are having a larger proof mass, we are having a larger sensitivity, but at the same time a lower resonance frequency, which is not very good. So a high sensitivity implies low resonance frequency, and therefore there is a trade-off required between the sensitivity and resonance frequency. So a typical example of a commercial device is an analog device accelerometer, which is capable of sensing an acceleration up to 50 g. As you may know, the acceleration is usually expressed in terms of g, the acceleration due to gravity. It has got a resonant frequency of 24.7 kilohertz. But the more important thing is it has got a full-scale displacement of only 1.2 micrometer. That is corresponding to this 50 g of acceleration. It gives a displacement of the proof mass of only 1.2 micrometer. And just imagine the kind of difficulty in sensing this small motion. So that is the basic challenge in the these kind of MEMS accelerometers. So this shows the application arena of MEMS accelerometers. We will not go into details of that. And this is the output voltage versus acceleration curve of a typical accelerometer. This shows a linear variation of the output voltage with respect to acceleration. Again, it is a linear sensor. So basically, such sensors we have also realized back in our organization, and they are surface micro machine structure. They consist of a polysilicon structural layer, and they make use of the principle of differential capacitive sensing, what is called, I will explain a little bit in detail. And they are having various ranges. They may be having various ranges. So here, to understand the sense structure or the sensor structure, basically we start off with a silicon substrate, and then we deposit, we are having a sacrificial spacer material, which is generally in the form of a deposited SiO2, and then we deposit the sensor material over that, and then we etch away the silicon dioxide so that we get a freestanding sensor material over the substrate. So as you can see, this is basically now a freely standing structure over the silicon substrate, and that is amenable to movement when you apply acceleration. So that is what is shown here. This is basically a sense structure which is a rust, that is, it is consisting of fixed outer plates, and then when the acceleration is applied, we can see that the proof mass, which is shown here, moves. It moves slightly, which leads to a movable finger moving in between two fixed fingers. Earlier we have shown two fixed fingers and one finger in between that. This movable finger moves in between the fixed fingers, leading to a capacitance change between these. That is, we are having a capacitance C1 between these two elements, which is less than capacitance C2 between these two elements. Why? Because capacitance, as we know, is directly proportional to distance between the plates. So as the distance between plates increases, the capacitance reduces, and as it decreases, it increases. The capacitance increases. So this differential capacitance is sensed by using electronic circuitry properly. So this is basically a microphotograph of our device, a 50G accelerometer which we have made back in ISRO. And this is the MEMS accelerometer chip in Toto, a photograph of that. And this is the package sensor. Now, as far as the analog device is concerned, it has also got the same working principles of a mobile beam and then fixed fingers and a mobile finger leading to a capacitance change. That is variable values of capacitance, which is sensed by using a suitable circuitry. Some details of which is given here, but we don't go into the details of that. The uh, process which is used in order to make this MEMS device is called IMEMS by analog devices, and it is a special process technology which combines the conventional CMOS electronics with surface micromachining. So that is what it does. So RF MEMS is another very important area where MEMS is applied to a large extent on RF devices, and they lead to high Q inductors, high Q capacitors, etc. There are a lot of RF devices which can be manufactured, and then there is something called inertial MEMS sensors, something called a gyroscope, which is used to measure rotation. So it is capable of measuring rotation or rotation rates, angular rate of rotation in the range of 150 degrees per second to 300 degrees per second. That is again a device from the manufacturer Analog Devices. And you may all know the overhead projectors that we use nowadays, even for film projections in cinema theaters. This kind of projectors are used, and the typical such an optical projector consists of an array of mirrors, as you can see here. So this was basically a MEMS technology, very successfully commercialized by a company called Texas Instruments. And there is an array of mirrors. Basically, what you can see is on the substrate, there is an array of mirrors which deflect suitably according to the need for steering the beam, and the optical beam will be steered appropriately with suitable color filters also in order to produce the image that we see on the screen. And this is an example of a chemical or gas sensor. It gives a single chip, a thin film chemical sensor array, and it is functionalization of CMOS electronics on a chip. And this is another very interesting application, which is something called a smart pill implant. And here what you can see is quite a large amount of circuitry, including some MEMS sensors, microfluidics. This is basically an area called microfluidics, where you take in some fluids and do some analysis on those fluids by using the by using the properties of silicon. So here we can see that the insulin dispensing is done based on a closed loop control by using these kind of smart pills. That is, this will detect that your sugar level is low, and then it will release insulin in a controlled way into your body in order to get a very effective treatment for the low sugar problem. And then this is an example of another device which is used for DNA detection from Hitachi. And this is an example of a device called a lab on a chip. Now, as you may know, when you go to a hospital with a certain ailments, then you are asked to do a certain set of tests like blood tests, urine tests, etc. Now, this is basically a device which helps to do all those diagnostics on a single chip. And how is this done? The analyte or the material to be analyzed will be introduced into some fluidic cavities inside this chip, where some controlled reactions also occur. And depending on the rate of reaction or the products that result from the reaction, we get an electrical output from this chip. So this is basically, so some electrical elements are also integrated along with this. And this is basically the technology called lab on a chip, which makes all this diagnosis and testing very affordable, very short time. Within a very short time, you can do all these tests, and probably they can be done even without much expertise. That is, they can be done in home also. So that is what the capability. Now, in the times of COVID also, we have seen that there are many, initially the testing was quite difficult, but now there are many test kits which are available even for doing testing at home. So that is the advantage that the MEMS technology or the microfluidics technology gives us. And this is a typical example of an aerospace application. Back in ISRO, we are having a project called Reusable Launch Vehicle or RLV. And here it consists of a lower booster stage and upper technology demonstration stage. Now, basically, this TDV, this aircraft sort of thing, is supposed to go to space, deploy a satellite or something, or take a human to space, and then enter back into the atmosphere and land safely on a high runway. So that is the basic end aim of this experiment. But here, basically, this is a technology demonstrator for that, and there you can see that the TDV vehicle itself, that is the small aircraft sort of thing that you see here, consists of about 700 parameters, requires about 700 parameters to be monitored. Of those, 200 temperature, 100 strain, and 150 health channels. So unless we are having miniaturized compact sensors, this kind of a mission is not possible. So this is a typical example of an aerospace mission which badly needs this MEMS technology for its realization. Now we come to the next part of the talk, which is introduction to nanotechnology. We are going to take a look at the nanotechnology. So again, the lecture by Feynman himself, the famous physicist, as we have already, I have already shown you. I can hardly doubt that when we have some control of arrangement of things on a small scale, we will get an enormously greater range of possible properties that substances can have. That is what he predicted. Again, in 1959, that plenty of room at the bottom, that lecture is again relevant in the case of nanotechnology also. So what is nanotechnology? It is engineering of materials and nanoscale in order to achieve useful functions. So in another other terms, it can be called a place for every atom and every atom in its place. So it is basically deals with the engineering of materials in nanoscale to get unique properties. So how small is a nanometer really? That is, the nanometer is basically the length your fingernails grow roughly in 1 second. In 1 second, you can imagine how much length your fingernails will grow. So that is basically the nanometer dimension that we are talking about. So the nanotechnology is the creation of useful functional materials, devices, systems of any useful size through control of manipulation of matter at the nanometer length scale. So there we exploit novel phenomena and properties which arise because of nanometer length scale. So that is the basic thing in nanotechnology. So a nanometer is 1 billionth of meter. A hydrogen atom is approximately 0.04 nanometers. Proteins are in the range of 1 to 20 nanometers in dimension. The feature size of computer chips nowadays has gone to 65 nanometer, that kind of a thing. And diameter of human hair is approximately 10 micrometers. So this gives you roughly an idea what nanometer is about. And the properties, when we tell the properties of the matter, when we tell it is the physical properties, chemical properties, electrical, mechanical, all these properties will change. And usefully making use of these functional properties is the main thing that we do in nanotechnology. So there is tremendous activity in nanoscience and nanotechnology, and nanotechnology consists of nanomaterials, nanoelectronics, nano-biotechnology. These are some of the major branches of nanotechnology, and there is a tremendous market for nanotechnology also. So let us look again at the basic theory. At the nanometer scale, properties become size dependent. That is the basic fundamental theory behind this. So we are having a higher surface to volume ratio. For a sphere, if we take the surface area to volume ratio is given by 4 pi r square divided by 4 by 3 pi r cube, which is directly proportional to 1 by r, as you can see. So the basic thing is that when you reduce r, we get a much higher surface area to volume ratio, and this leads to some property change in the materials. So for example, thermal properties like melting temperature will change, mechanical properties like adhesion, etc. will change, optical properties like absorption and scattering of light will change, electrical properties like tunneling current will change, and magnetic properties such as paramagnetic effect will change. So basically, when you are having this higher surface area to volume ratio, the properties of the matter will change. That is what we are using here. The ancient Romans, by the world's early nanotechnologies, they made out some process to make red glass, etc. So this is all about the history of nanotechnology, and the traditional Indian bhasma preparations, which are used for some Ayurvedic treatments, perhaps, are shown to contain nanoparticles. So this is perhaps the world's first nano product. Can you make out what is the nano here? It is basically the thing that is applied over the eyelashes, that is darkening around the eyelids. that we used to call ITEX or Kajal, which was invented very early in India, introduced in India around the year 1938 itself. Basically, it uses nanotechnology in order to for its realization. So it is composed of nanoparticles. So many existing technologies already depend on nanoscale materials and process. In existing technologies using nanomaterials and process, we are able to come up with new materials, and we are having the ability to design more complex systems in the future also. So what is special about nanoscience? Atoms and molecules are generally less than a nanometer, and we study them in chemistry. Condensed matter physics deals with solids, and nanoscience deals with in between the meso world. So size-dependent properties is what nano technology basically addresses. As we have already seen, the surface to volume ratio in the case of a 30 nanometer particle, only 5% of particles are on the surface. In the case of a 10 nanometer particle, 20% of the atoms are on the surface. And in the case of a 3 nanometer particle, 50% of its atoms are on the surface. So this is the important thing. As we reduce the size of the particle from 30 to 10 to 3 nanometer, we can see that the atoms which are present on its surface go up from 5 to 20 and then to 50. So this is what makes the new properties possible. So nanotechnology enables discrete control of desired material properties, mechanical properties which are dictated by particle grain size, thermal properties, emissivity influenced by particle size, thermal conductivity also influenced by the particle size, electrical properties such as nanostructure and defects, then high aspect ratios enhance field emission, then optical properties such as transparency and color, then photonic band gap also. So these kind of materials change according to the nano particle dimensions. So they can show different properties as we have already seen. We will not go into much detail. So this is a typical example of a silver spheres. So as you can see, what is shown on the left in red color is 100 nanometer silver nanoparticles. And then as we progressively reduce the nanoparticle dimension to 50, 120, 80, 40, etc., as we change the nanoparticle dimensions, we can see that the silver nanoparticle takes, or the silver material takes different colors. So this is a typical example of an optical property which is getting influenced by the nanoparticles which are composing the material. So basically here what we are saying is the color changes. So that is one of the offshoots of nanotechnology. Now these are some commercial aspects of the nanotechnology which we will not go into much detail. And now we come to nanotechnology applications. So in the chemicals and materials area, they are used in catalysts, membranes and filtration, coatings and paints, abrasives, lubricants, etc. And then in the medical and pharmaceutical arena for detection, analysis and discovery, drug delivery, as we have already seen, is a very promising area. Like for example, nowadays there is discovery that if you introduce these nano particles, they can go to the appropriate site where the drug has to be delivered. For example, in the case of tumors or cancerous diseases, basically what they do is that a solution with suspended nanoparticles is introduced into the body, and when these nanoparticles can then be steered properly by using some magnetic material at the kept outside the body, and then we get the ability to steer those nanoparticles to the appropriate point in the body or appropriate area in the body where there is a problem, and then they can deliver the drugs appropriately. So that is becoming now very advanced method of treatment. So over 50 components, automobiles and transportation area, over 50 components of automobiles are affected. Structural materials, coatings, sensors, displays, etc. These are all the areas where automobiles get an impact. Then in the IT and telecommunications field, photolithography, electronics and optoelectronics, process, data storage, quantum computing, wireless technologies, all these are getting influenced. And the case of energy is one of the very important application where we are having things like fuel cells, solar power. For example, some of you might have read that the solar panels, when we coat it with a suitable nanomaterial or nanoparticle, we get a higher efficiency out of solar cell. So that is a typical example of a field in the field of energy where the nano technology is able to play a significant part. Then batteries, power transmission, etc. So some of the products where this is used the razor blades, the golf balls. So these are all some examples of common commercial products where this finds significant use. Then the coating for the automobiles, as we have already told. Then super hydrophobic coating, so for some of our plumbing fittings. Then fabric treatment, that is the treatment of clothes by using this. Then antimicrobial coating on refrigerators. Then photocatalytic coating on windows. Then body moldings for these automobiles. Then OLED display. These are all examples. OLED display for this camera. So these are all examples where nanotechnology finds a lot of use. And in many of these products, the introduction of nanotechnology brings down the price also. It doesn't become more expensive. The price comes down from 35 to 11 percentage kind of thing, and that makes the products cheap also. So this is again another example where we use windows by using which use the nanotechnology property. And this is a graphic depicting the financial side of this. And then there is a conductive adhesive filter which makes use of nanoparticles. Then there is a reactive foil for room temperature soldering, which again makes use of the technology. Heat transfer materials is another very common application where nanotechnology is used. And how does it help? We can see that we get a more surface area of contact if we use nanotechnology in this case. And therefore, a more efficient heat transfer is achieved by using this. You might have seen that even in computer boards, we are having the heat sink, which is used to conduct the heat away from the processor ICs, and they can be done by using this kind of technology. So nanotube enabled memory and logic chips are also very common. And another common application is flexible electronics, which is conformable electronics. As you can see here, it is a bendable electronics which is fabricated on a bendable substrate. So what is basically the advantage of it? It gives us the power in the sense that it leads us to displays that are foldable. For example, a TV display itself, if it can be folded like this, then you have immediately got the prospect of a portable TV. So now let us see some of the applications in space, that is for aerospace and defense, as we have already seen. The structural materials, coatings, fuel, electronics and electromechanical systems, weapons, these are all the aerospace applications. So why do we use it? We increase spacecraft and launch vehicle capabilities with simultaneous reduction in weight and cost. It gives us a reduction in both weight and cost of the launch vehicle. So how is this done? Lighter and efficient structures are used. Then integrated sensors are used for online health monitoring, miniaturization of systems, and efficient and lightweight power supply. These are all the areas where we get a good advantage out of this technology for aerospace applications. So taking a typical look at a launch vehicle, for example, the GSLV Mark III launch vehicle in the case of ISRO, the nanotechnology basically leads to better structures. That is basically structures which are having very high specific strength, high fracture toughness, easy fabricatability, and exceedingly high demand on reliability. So they are very cost effective also. So it leads to structures which are very versatile for the aerospace applications. Similarly, world over also, quite a large number of applications are there in the aerospace arena. I will not go into many details of this. You can take a look at this later. If you can contact me, I can give you further details also. So this again, the worldwide scenario, which shows that it can be used in space systems such as nano-satellite constellations, nano-satellites, in space subsystems for heat exchangers, scanning probe devices, then batteries and fuel cells, and then in components and materials such as in CNT composites, nanomotors, all these kind of applications. So it is used in structural elements for spacecrafts and launch vehicles, thermal management systems, advanced energy systems, advanced propulsion systems. All these areas, the nanotechnology finds a significant use, and it has got advantages in each of these areas in its own way. It gives advantages in its own way. So the nanomaterials that are basically used, nanoparticles, they are in the form of nanoparticles, nanocrystals, nanopowders, nanotubes, nanowires, and nanofibers. And the requirement for space applications, the requirement of this for space applications, as we have told earlier, lightweight. They lead to lightweight structures, radiation protection, good electrical conductivity, thermal conductivity. They can be used for sensing and health monitoring. They can be used for self-healing. That is, if there is a structure that is damaged, they can be used to self-heal. Then energy generation and energy storage. These are all the applications. So again, it becomes tremendously important in the case of the reusable launch vehicle technology, which we have told earlier. And there, as I have already told, this is basically a vehicle which deploys a satellite and then re-enters back into Earth's atmosphere and lands safely in the runway. So the space shuttle of NASA, you might have heard, that is one such vehicle. But here the important thing is that it should be able to withstand the heat on re-entry. So there is a very high thermal energy which comes on the vehicle during re-entry, and the withstanding of this thermal energy is done by using what is called a carbon nose cap or nose cone, which is basically an application of nanotechnology. So again, another array of applications: quantum dot-based solar cells, supercapacitors, hydrogen storage materials, and then nanomaterials in lithium-ion batteries. Supercapacitors are also made possible. What are supercapacitors? Basically, they are capacitors which are capable of delivering a high energy instantaneously. And they can be used in some of the applications in place of the batteries that we generally use. So then nanofluidics, which are used for thermal management of spacesuits. As you may know, when humans are going to space, they require spacesuits. You must have seen the astronauts going into space. They are all clad in spacesuits, and in order to get good thermal conductivity from the spacesuit, we need these nanoparticles as base fluids. So that is another important application. Then a thermal management system, which is again about the heat dissipation. Then advanced spacesuits for astronauts, as we have already seen. Then a propulsion system which is based on carbon nanotubes has also been proposed. CNT is nothing but carbon nanotube. As you might have heard, the propulsion system leads to a higher specific impulse, which gives a higher impulse per unit weight of the fuel. And this basically leads to better propulsion systems for the launch vehicles as well as the satellites. And there are spin-offs from the space area also. One basic thing is polymer nanocomposites with improved barrier properties and packaging materials. Then CNT fibers and fabrics, photovoltaic cells, and hydrogen generation applications. So these are other space applications. And this shows this is one photograph which shows where all the nanotechnology can be used on a space vehicle. So this is another graphic which shows the impact of the technology, shows the impact of MEMS technology also on the space vehicles. Now let us see the scenario of nanotechnology research in India. Basically, if we see, the nanotechnology opportunities are basically meeting energy needs with clean solutions. So that, as we have already told, meeting our energy needs with the clean solutions. That is one of the areas where nanotechnology can play a prominent role. Then maximizing the productivity of agriculture, that is another important area. Then providing abundant clean water. So providing clean water is one area where nanotechnology can play a really meaningful part in the form of filters, etc., which are highly efficient. In the case of power also, the solar power, as we have already told, the solar panels which are highly, which become efficient by using the nano technology and nanomaterials. Then making information technology ubiquitous, enabling development of outer space, increasing the health and longevity of human life, networked electronic sensors for improved security. These are all the opportunities for nanotechnology in India, basically. So nanoelectronics, if you see the advancement of nanoelectronics in India, we started off with manufacturing individual germanium and silicon transistors, and then we use TTL, and then we started using TTL and metal gate CMOS devices. Then Texas Instruments set up their first design house in India in 1985. There was a semiconductor laboratory which was set up in 1977. It was envisaged in 1977, set up and commissioned in 1983. It used to produce 5 micrometer silicon gate CMOS. So these were the major attempts of India in the semiconductor fabrication area. So the status today is that the SCL foundry is upgraded to 0.18 micrometer CMOS, that is the semiconductors lab in Chandigarh, is one major manufacturing facility for microelectronics in India, and it comes under our department, that is Department of Space, and the foundry there, the fabrication facility there is upgraded to 0.18 micrometer dimensions, capable of supporting 0.18 micrometer VLSI devices. India is an important chip design hub, though. Even though our manufacturing capability fabrication capability is relatively less, we are having quite a number of chip design houses. And then there is a government semiconductor policy also, which was announced in 2008. But chip fabrication is set to come off in India in a very big way. So design is happening quite a number of places. Like we are having the multinational companies like Texas Instruments, Analog Device, etc., whose major design houses are there in metro cities such as Bangalore, and in our academic institutes like IITs, IACs, etc. Also, a lot of research is being carried out in the area of the MEMS, VLSI, and nanotechnology. So they get the devices fabricated basically from the foundry houses in Europe, which are used for academic purposes. So semiconductor manufacturing provides key background knowledge for nanoelectronics and other nanotechnologies. So we are having something called the Indian Nanoelectronics Users Program, INUP for short. It was launched in 2009. It is a facility that is fully commissioned now and fully functional, with IIT Bombay and IISc as Bangalore as the nodal centers. And the goals of the program are to disseminate information on nanoelectronics, generate widespread hands-on experience, and run the facility as a service provider for other aspects in the country. So basically, from the academic arena, what you can do is, if you are having an idea about a particular device which can be manufactured, or a particular MEMS device or nanotechnology device which can be useful or which can find a potential application, then you can propose it as a project, and then you can take up this fabrication of this device, as well as the simulation and characterization of these devices with the help of these nodal centers at IIT Bangalore and IAS. So that helps you to try out some of your ideas in this area, like MEMS and nanotechnology. Experimentally try out these devices and then characterize them, and then make them useful in commercial products. So that is an important initiative that the government has launched in order to bring the nanotechnology to the popular, to make it popular among the academic institutions within the country. So now we come to the concluding part. Basically, integrated MEMS and nanotechnology will revolutionize the technology in 21st century, similar to silicon digital revolution in the last century. In the last century, we know that there has been quite a rapid advancement in the silicon IC technology. So the same kind of impact the MEMS and nanotechnology is going to have in the coming century, and it will lead to the same kind of versatile devices, powerful devices. The resulting integrated products, as we have already seen, will contain multiple energy domain components. So this is another major important thing for these technologies. They contain multiple energy domains, like they contain mechanical domain components, they contain electrical domain components, they contain optical domain components, chemical domain. So they therefore provide some exciting system solutions in the near future, as we have seen various applications such as mechanical sensors, optical projection systems, then the chemical gas sensors. All these are some of the system solutions that these technologies enable us. Then micromechanical and microelectromechanical and nanotechnology enabled systems have evolved. They have already evolved to support seamless integration of different domains like mechanical, electrical, fluidic, magnetic, etc. And thus they enable the realization of high performance, low power, low cost, and reliable smart systems for a number of application domains, including aerospace. So in aerospace also, we have seen that significant number of applications are there, which leads to, as we have seen, weight reduction, size reduction, power reduction. So all these are, and to tell you one typical example, we are having a fuel cell project back in ISRO, which we have initiated now. And as you may know, fuel cell is a very clean source of power, and it leads to basically a zero emission product where water is just a byproduct and hydrogen and oxygen are combined in order to get the fuel. So that is again a very promising technology which we have tried, and this MEMS and nanotechnology has got the capability to impact the efficiency of those fuel cells and the fabricatability, that is the ability to fabricate those fuel cells in a very good manner. So these technologies are, as we have seen, are got applications in a large number of pervasive areas. So this is some additional resources which you can possibly refer to. There was a proceedings of IEEE in August 1998, and then November subsequently, November 2003, which deals exclusively, a little bit old publications, but they deal exclusively with the review articles. And then there is quite a lot of work going on in universities worldwide also. There is something in USA called National Nano Fabrication Users Network, NNUN, established by the National Science Foundation USA, and the participating universities are Cornell University, Stanford University, Penn State University of California, Howard University. Similarly, a good amount of work is being carried out at MIT, University of Illinois, at University of Washington. Then companies like HP, TI, analog devices, etc., are also making a number of products. As you might have seen, the analog devices makes this accelerometer and the gyroscope ICs, and they are one of the fastest selling MEMS products that are available in the market and commercially successful products. So with that, I basically come to the end of my talk, and let me see whether I can show you one video or so. I'm not sure whether it will play correctly, but let me see that now. Please hold on for a minute.
So overall, our lab is interested in how the brain adapts to the novel
Are you able to see my screen?
Yes, sir.
Yeah.
Yes, sir.
So what we've been trying to do is develop technologies that are small, but would be important. And right now, the really concerning aspect of the hypertension problem. And basically, it means that there's elevated pressures inside the skull. Why that occurs, we don't really know, but when you're in microgravity, you don't have gravity pulling the fluid out of your head and down into your lower extremities. If you look at videos, you'll see the full face syndrome of astronaut, and so that may be a contributing factor. What they've seen is that it deforms the eyeballs, and so get nearsighted. And currently, the only measurement they have for that is ultrasound, and it is only a relative measure, so it can't give us the kind of direct pressure measurement that we would like. So our device will allow us to...
There's some sort of a portable brain scanner which has been developed by using these technologies. It is used in the International Space Station,
shine near-infrared light into tissue,
and it of course finds use for terrestrial applications also.
Non-invasive places on the skin, but it does allow us to make a research of the brain with sensitivity that is pretty close to that of MRI. I have taken it home and just tested it on several occasions. And it is amusing to be able to, say, have brain scan a low travel. The ultimate goal is to have a very low profile sensor net that will fit over the head and cover easily and comfortably, and then just have a separate box with the hip that goes in the pocket that does all the recording for it. And then we're developing a system that goes with that that will automatically detect such devices, connect with them, and acquire the data for your use or for the physicians. Personally, I'm most excited about being able to do the brain imaging and the brain monitoring in more remote settings. or you can take it outside of the normandie center like we have here, and we can go either into homes or we can follow people through a 24-hour day, and we can actually get monitoring more continuously and in more realistic settings. And of course, we're very excited about the possibility of spaceflight and being able to fly these one day.
Okay, so that was about a portable brain scanner which can be used, which is presently being used in International Space Station, and it can be used for terrestrial applications also. And it makes use of the MEMS technology in order to realize these small sensors which pick up the biomedical signals. And let me see whether one more video I can show you.
In a complex engineering system, it's critical to understand how all of the parts are functioning at any given moment. When that system is in a harsh environment, it becomes even more critical. Imagine if you had a way to constantly monitor the system, regardless of where it is. For a number of its systems, NASA has relied on a small company in Conroe, Texas, to provide monitoring solutions. Infocon has been developing miniature, low-power, wireless data acquisition and communication systems since the mid-1980s. Early on, the company's president, Carl Kiefer, envisioned putting a network of sensors on a NASA structure.
This is basically on a network of sensors which are used again in International Space Station. A network of wireless sensors.
And those astronauts are floating around putting those sensors on the space station. Anyways, 12 years or 10 years to the day later, we actually watched the astronauts live. We put our system installed.
So basically, when an astronaut is doing an extravehicular activity, what is called by an extravehicular activity, then some wireless connection is required with the astronaut. So that is what this sensors accomplish.
And verifies the station's integrity while it's in orbit. The firm is now building ERIS that will go on the ends of the station's solar array trusses to monitor the impulses that occur whenever the station is reboosted or has a docking. Kiefer compares the impulses to a tuning fork.
Get a tuning fork, breaks for a while, and it stops. So you can think of us as the ear that listens to the tuning fork response of the space station.
The ERIS will record the microgravity changes to the nearest half a millionth of a G when the station experiences such an impulse. Because of its success with monitoring technologies, Infocon was tasked to design a number of systems for NASA's return-to-flight shuttle mission STS-114. In fact, the firm actually had 4 different monitoring systems on board, and all 4 had their genesis in the SBIR program. One system monitored the leading edges of the shuttle wings for impacts. One monitored the stresses on part of the main engines during launch. Another monitored payload vibration during launch and landing. And another monitored temperatures during the thermal protection system.
So these are about the various sensors which were used in the space shuttle system. And they used MEMS technology as well as wireless technology in order to enable some of the very special monitors.
Although Kiefer was happy with all of their monitoring systems, he was especially happy about fixing that glitch.
I was proud of that I wouldn't have been had things just worked perfectly because it was like Apollo 13. Not only did you do it, you saved the day.
Infocon is working with NASA on other monitoring solutions. They're collaborating with Johnson Space Center and the Navy to transition some technology to NASA that was originally developed for the Navy. The technology can map the spread of a catastrophic event, such as an explosion. Under an SBIR contract from Langley Research Center, The firm is developing technology that can identify the area of an impact on any space vehicle. As NASA continues on a journey of exploration, Infocom will work on providing solutions to monitor the agency's new systems and structures.
Okay, so that is all. Now I think we have more or less come to the end of the talk.
Thank you, sir, for the wonderful session.
Right.
And participants, if you have any further questions, you can ask sir. Um, if you have any questions, you can write in the chat box. Sir can answer that.
Any particular project in which you are interested also, you can later, if you want to, we can have a discussion so that.
Sir, can we share the email with the participants? Your email?
Yeah, sure.
Yes, sir.
Any queries regarding?
Sir,
work
here Ritan has a question. What are the future scopes in nanoelectronics in India specifically? And
I didn't get you. Can you repeat?
uh, sir, what are the future scopes in
Yeah.
nanoelectronics?
Nanoelectronics. As I already told, nanoelectronics is a very growing area and it enables the highly miniaturized realization of these systems. And as you may know, we are nowadays more and more in need of computing power. For example, we are right now having these tiny smartphone devices and iPads, etc., which is capable of playing streaming video. So this is a technology which came up recently only, like maybe within the last 5 or 7 years, and that has been enabled to a large extent by the nanoelectronics. That is the basic processors, which are processor ICs, which are there inside this. I don't know whether you know the processor devices inside these smartphones, iPads, etc., are realized by using technologies such as 65 nanometer also. So they make use of technology having dimensions of 65 nanometer, which is well into the nanometer regime. So we are already seeing the impact of nanoelectronics that way, and further more complicated applications are also going to come up, like in the case of quantum computing, then the very fast image processing, supercomputing. All these are applications where the nanoelectronics is going to play a very big part because of the its ability to give us devices which are very small, but at the same time those devices are having a very high speed and a very low power consumption. So these are definitely some of the applications which are going to come up in the future, like quantum computation, supercomputation, image processing, and one of the another important area nowadays, which in India also there is a lot of stress, is artificial intelligence, as you may know, and this artificial intelligence requires a lot of complex computation in the form of artificial neural networks, etc., and a lot of data also used to train those artificial intelligence engines, and that requires nanoelectronics. So the area of application for nanoelectronics is quite lively and exciting.
Sir, another question is from a attendee is, sir, will the future medicines be based on e-pills, based on nanotechnology?
Yeah, that is what one of the slides which I showed, that implant pill. So that showed basically a pill which can be taken, which is taken into the human body, and then it does a controlled insulin dispensing. So such applications are already there, and as I told, in the biomedical area, the detection and treatment of cancer, for example, is another major area where these bio pills and other things are going to play a major part. Similarly, nanotechnology also. These nanoparticles will be introduced into the body, and then they can be steered appropriately through the body and then they will reach the exact site of the cancerous growth or whatever. I'm just telling an example, and then they can dispense some medicines at that particular site. So you don't have to expose the entire body to these chemotherapy and those kind of damaging treatments. So it gives us the power in order to do treatment at a very specific sites in a very controlled manner. And there is something even called nano robots, which are basically small nano machines which can be introduced into the body, and then they can be propelled by using a suitable magnetic field or something which is kept outside, and then when they are propelled into the appropriate areas, they can do the treatment. That is a more focused treatment. So these are basically some areas where a lot of revolution or revolutionary advancements are happening in the biomedical area. So monitoring of vital signs, then effective treatment, all these are areas where a lot of applications are going to be there.
Sir, another question is, what are your thoughts on IoT or ML being incorporated in nanotech? This is a question from another attendee.
Yeah, IoT is again another very important area nowadays where you are using quite a lot of sensors in order to study a particular environment. So you dispense all these sensors into the environment, and then naturally, if they have to be very small and they have to be low power consuming. Otherwise, it is difficult to find the energy for all these sensors to work. And so IoT is a very important area. For example, it is used for environmental studies, studies of global weather phenomena, all these kind of areas. So that is, and then this machine learning concepts, as we have already seen, it requires quite a lot of intelligence and quite a lot of computation power in order to incorporate this machine learning into the IoT devices. And if you might have heard something called edge computing, it is a technology where the electronics or the computational power is put into the sensors. That is, the sensors are the edge devices, and by putting suitable computational power into these edge devices, we gain a lot of advantage. So such kind of applications are also envisaged in this area. So that is quite a growing and promising area of work.
Sir, another question is, can we see small scale quantum computers for general use? It is a question from our another attendee.
No, can we see small scale?
Can we see small scale quantum
Just give me
computers?
a minute. Please give me a minute.
Yes, sir.
Yeah, please, can you repeat?
Yes, sir. The question is, can we see small scale quantum computers for general use in future?
Now, quantum computing is another very promising area of research, but introducing it into practical domain, we have had limited success only till now. Like to get the quantum computers that are really useful, a lot of research is going on, and there are companies which have produced some products, but to realize its full initial promise, such devices or equipments have not been commercially available, because as some of you may at least know, one of the major things is for quantum computers, they require cooling. Till now, we have not been able to come up with quantum computers which can do functionally or which can function effectively under room temperature kind of conditions. So that is one of the major problems which the research people are fighting against, and we hope that many of these challenges can be overcome, and then quantum computing will come up in a big way, which will make some unique solutions possible. Like, for example, a very quick simulation of the some of the problems, like for example the global warming, all those kind of things which require, which are not, which cannot be accomplished by using even supercomputers as of the present. Quantum computing is supposed to make all those things possible, but the technology is set to come into some sort of realizable practical application now also. So there are still open research problems which have to be solved. Yeah.
Thank you, sir. Another question is, sir, I was also going to ask the same question, that what are the future scope of microprocessor industry in India?
Yeah, that as you may know, it is an ever-growing field. We have not come to a stop, even though the laws like Moore's law, etc., which people tell have come to a slowdown. We have not yet come to a stop in the processor arena. That is, processors are evolving now also. Like for example, the Intel company itself, which introduces the processor, or which makes the process for the personal computers, that is going on evolving, even though it may not be in the strict sense of VLSI integration. There is an evolution taking place in this process in the form of parallel architectures, in the form of 3D packaging, in the form of new device structure for the VLSI circuits. So all these are areas where a lot of advancements are still going on, and we have not yet come to a state where we see a stop in this growth. So that we don't know whether it will happen maybe 5 or 10 years down the line when we come to devices that are in the atomic dimensions. But now also the industry has been able to pursue this integration very aggressively in order to come up with more and more functionalities into more and more miniaturized devices. Yeah.
Sir, can India, we can see India is advancing in the microprocessor, not only design,
Yeah.
but also manufacturing, like
I,
China.
that is one thing which I told. Manufacturing is set to take off much in our country. That is
Yes,
a little bit. We are yet to catch up with the rest of the world. For example, China is one nation which is doing, which was as backward as us, but which has now started doing relatively well. So we are yet to come to that kind of status. So that the different people like government and industries are also making an effort, but anyway, basic hope is that we will turn around. For example, the semiconductor lamp, which I told you, is now making many of the ICs for our use. So at least in the strategic and defense applications, we are having some of our key needs fulfilled by those the semiconductor lab. So we hope that in future also, that such kind of application houses we will be able to set up. And then one of the major reasons there is the capital intensity, that is the capital intensive nature of this industry, which requires for the sophisticated manufacturing a very high investment. So that is one of the major reasons of the of introducing it, or difficulties in introducing it, and probably we will be able to overcome it, and at least some of our key applications and for some of the experimental work and some of the new technologies, we will be able to tap this application capability.
Sir, another question is from our participant is, what are your views on the Shakti processor designed by IIT Bombay?
Yeah, that is actually a new processor venture which has been fabricated in a semiconductor lab. And as I understand, it is a powerful parallel processor, and it makes use of the new processor design paradigms. It has come from IIT, and therefore its design is a quite exciting one and can be used for many major applications. I have not personally gone through the details of the design, etc. But what I came to know is that it is a powerful processor which can find quite a lot of applications in aerospace or in other processor compute intensive fields.
Okay, sir. And sir, for another question, I I'm preparing for my GATE exams. I am in final year. I want to study VLSI engineering.
Yeah, yeah.
So if I do my MTech in VLSI, so I can uh, specialize in MEMS MEMS technology in
Yeah,
future.
yeah, yeah. For those students who do VLSI, MEMS is an area where you can specialize because you get an interdisciplinary exposure also, as we have told in our talk. So it is basically an interdisciplinary area, and as you know, the engineering in the modern times is going the interdisciplinary way. So you get a very good exposure to all the some of the major fields of other areas also or other disciplines also, which will help you in a long way, like for aerospace applications or for automobiles. So all these are areas where you need an interdisciplinary vision, so to do useful engineering work. So that is going to help you in a long way. And MEMS is an offshoot of VLSI technology, and therefore it is basically it's a natural specialization of the VLSI uh, technology
Yes.
for VLSI students.
Sir, another question is from our attendees is Shakti processor is comparable to Intel processor in terms of day-to-day computing?
That is why I have not done a personal study on that. But basically, what is the architecture and for what it is really meant? Is it for image processing? All those kind of things have to be seen because it depends on the kind of architecture. So it may not be very right to tell that it can be compared with Intel processors because Intel processors are basically for the as the mainstream processor for PC applications. That may not be the case when you want to design your own processor. So the way the Shakti processor is architected and its primary, what are its designers, what were the main vision which the designers kept in mind, that is the major thing. So, for example, you can have a processor for image processing, which is specifically suited for image processing tasks. So that is the kind of thing. So it may not be really correct to compare one processor with another unless you know that they are done on the same technology with the same application area in mind.
Yes, sir. And another question is for attendees is can you share your thoughts on how ISRO is utilizing the nanotechnology for space flights and what can we expect in this regard for the future?
That is what one of the major areas is the application of nanotechnology for the structures. That is one thing which I showed prominently. That is nanomaterials which are used to make the structures of the launch vehicles and the satellites. So that especially makes it possible to make lightweight, highly reliable, and high fracture toughness or rigid structures that are made possible by using the nanotechnology. Then there is another example which I showed in the case of that reusable launch vehicle. When it makes a re-entry into Earth's atmosphere, there is a terrific amount of heat that is generated. So in order to withstand this thermal energy or thermal heat dissipation, we need very special materials like carbon materials, etc. And there are also the nano materials like those which are constituted out of carbon nanotubes, etc. They make possible these highly heat withstanding structures or thermal withstanding structures with a lightweight and good rigidity. So that is those are all examples where the nanotechnology, nanomaterials, etc. are used. And then in the energy domain, in the propulsion domain, we have seen it leads to high efficiency propulsion. Then in the energy domain, one example which I told you in the case of fuel cells, it leads to better efficiency fuel cells. These can substitute for our batteries. So the heavy and bulky batteries that we use in launch vehicles. So these are all some of the applications of the technology where we can gainfully use them. And we are in the process of inducting some of these into our programs also.
Thank you, sir. Is there is not any more question? And yes, another
So
question is
you
here.
can feel free to contact me if there is anything else right now.
Yes, sir. Then I am sharing your email in the chat box.
Yeah.
Uh, Participants, if you have any more questions, please contact. Please email sir in his. I am sharing his email. Please wait a second. Uh, uh, I have shared the email address. Sir's email address. You can contact with sir,
Yeah.
and sir will obviously. Uh,
Okay, so thank you
Okay.
for this opportunity. It has been nice
Thank,
talking to
sir.
you.
We are very honored to have you here for spare your valuable time. I just want to present. Uh, One second. Uh, One second, sir. Mm, just a token of appreciation from our end. I am just sharing the poster with
Yeah.
you right now. Uh, we are very honored to have you, sir, here. It was a wonderful session for us. Is my screen visible, sir?
Yeah, yeah, it is visible. Yes. Yeah.
Yes, sir. Thank you, sir,
Yeah.
for sparing your valuable time. I will send it to you later email
Yeah, yeah,
in
right.
email.
Thank you.
Thank you, sir. Thank you again, sir. We
Right.
are honored to have you here.
Okay. We will close now.
Yes. So, thank you everyone for joining this session. And if UEM students, you can stay here for a minute. I have a announcement here, and those who are not students of UEM, you can leave now. So.